Good morning, everyone, and welcome to today's workshop. So as you know, we will have our second day of this marine data for sustainable oceans, and this is a Copernicus Marine Service workshop, and today we will have the practical session. So as you know, 2 days ago, we gave you an introduction to the Copernicus Marine Service, and today we will have the session with the demonstrations and the tutorials. So we will show you how you can visualize the data sets and how you can apply it to a case study. So before we start, we are going to go through some house rules and guidelines to help you follow this workshop in the best possible way. So first, please do not use the chat that you see on your right-hand side for your question. You can use it for small talk or say hello to us. But if you have a more technical question or if you have any other type of question, we will use the Q&A section on the website. So you can find it on the top bar of the event web page, and you will see a section dedicated to the Q&A, and that's where you can ask your questions to the speakers today. And next to it, you will also see an area dedicated to the polls that you can answer at any time. Concerning the agenda of today, we will have 4 presentation and demonstration. So I will be the moderator, and then we will have a demonstration of the Copernicus Marine Toolbox by Rezak from the Mercator Ocean user support. And then we will move to the tutorials demonstration by the novelties team. So Alexandre Merin will do the Jupyter Notebook tutorial. Then we will have Daria Andrievska that will do the QGIS tutorial demonstration, and we will end with Simon Millet for the RStudio tutorial demonstration. So as I said, it's the practical session. We hope you had time to try on your side the tutorials that we made available for you and that you have some questions. And yes, so we will go to the first presentation, which is the Copernicus Marine Toolbox. So Rezak, whenever you want, the floor is yours to start your presentation. I was going to say, yeah,
Thank you, Gael. Good morning. I will share the screen. Can you see my share screen?
Yeah, we can see it. Thanks.
Perfect. So good morning, everyone. For those who didn't attend my first presentation 2 days ago, I'm Rezak from Copernicus Marine User Support Team. Today, I will be presenting the Copernicus Marine Toolbox, which is also used to remotely open and download Copernicus Marine data. So let's dive into it. So Copernicus Marine Toolbox is an open source package which is used to retrieve various metadata information available in our catalog. It also allows you to download subsets of data sets by extracting only the parts of the data that you need. Copernicus Marine Toolbox also offers you the possibility to download the original files, the data in their original forms. And another advantage of the toolbox is that you don't have a memory limit when it comes to downloading the data. And like when using the graphical interface here, as long as your machine can handle the memory, then you are good to download the amount that suits you. So another advantage of the toolbox is that it allows to optimally and parallelly download the data. This is due to the conversion of the data to the analysis ready cloud optimized format, the ARCO format, which means that the data has been homogenized for ease of use and interoperability. Cloud optimized, which means also that the data has been optimally stored, which allows the fast and the parallel access to it. The toolbox also offers various services. So we have the ARCO GeoSeries service, which is optimized to analyze larger geographical area within small period of times. And we have also the ARCO time series service, which is optimized to analyze small geographical area within big period of time. And we also have the original file service, which allows you to access to the data and retrieve it in its original form. So the Copernicus Marine Toolbox also offer various functions to execute it. So first we have the login function. So with this one, you can log in and begin downloading your data and also remotely open it. And when executing the login function, you will be getting an automatically generated file which contains your credentials. We have also the describe function, which allows you to retrieve the metadata related to the data that you wish to explore. And the particularity with this one is that it doesn't require you to be logged in. And then we have the get function, which allows you to access the file browser service and get the data in its original form. And we have also the subset function, which allows you to retrieve only subset of data by selecting only the needed parts. To execute this function, you can use two different supports. You can use the command line interface, like in my case, the Miniforce prompt, or feel free to use the prompt that suits you. You can also use the Python API interface, application programming interface, and for that, you can use Jupyter Notebook, for example, or Visual Studio Code, or any other editor that suits you. So now let's take a look on how to get started with the toolbox. So first things first is that you can access our website and go to the user support section here, and then go access our help center and FAQ section. Here we'll be getting various articles which speaks about various topics. The section that we need to access is Copernicus Marine Data Download, and you click on it, and here you can see also that you have various topics, and the one that you need to access is the Copernicus Marine Toolbox section. So once there, you will be finding various articles which speaks about on how to get started first with the toolbox and then how to use it with examples. So let's say the first section here, we have an introduction article, which basically defines the toolbox and how to use it in general. We also have an interesting article which speaks about on how to install the toolbox with the steps listed. Of course, as the user support team, always recommend installing the latest version of the toolbox. And for that, we always recommend using a Mamba environment. The advantage is not only you would get the latest version of the toolbox, but also you will prevent all the errors related to the dependencies, dependencies conflicts. Here in the main functionalities, we have also various articles which speaks about on how to use the function that I have presented, the subset function, the get function within the two different supports, the command line interface and the Python API interface. We also have some use cases articles here, which speaks about how to use the toolbox for those who wish to go further and take a look at different examples in which you can use the toolbox. And also for those who don't wish to work with Python, the toolbox is also available and you can work with it using R, for example, or MATLAB. Troubleshooting and FAQs contains also some interesting articles. The one that we recommend to consult is the troubleshoot articles, which contains the common errors that can occur when installing or using the toolbox. So if you encounter an error, you can consult this article, take a look at the common errors that can occur and with an answer to it. So it's always a good thing to consult it in case you have a given error. Reporting an issue or a feature request speaks about how to report an issue or a feature request and list the steps to follow. Next milestones and roadmap present the breaking changes that will occur in the future releases of the toolbox. Of course, here we have an archive to the toolbox, which is basically a set of articles which speaks about the previous version of the toolbox. Of course, as I said, we always recommend installing the latest version to get the full access to our data. And if you need further assistance, you can go to the message icon here and go to the news icon, for example, and take a look at the latest version of the toolbox. You scroll down, you're going to see that the latest version is the 2.0. Also, we can go to the help here and type in your research in our help center. And then let's say, for example, you can type in toolbox introduction. You will be getting the article corresponding to your research. And of course, if you need further assistance, you can go to the message icon here, click on it, and ask your question to our chatbot Blue. So let's say I want to ask a question, how to use the toolbox. So what Blue is going to do is that he's going to explore our data center, and we try to come up with the best suitable answer for your question. And Blue is optimized in such a way that he always came up and join sources at the end of its response. These sources will guide you to the related articles, which you can consult and find the best suitable answer to your question. Of course, if the answer doesn't satisfy you, you can always go with the talk to a person option, click on it, and you will be redirected to us, the user support team, and we will be glad to help you out. So now let's say that you have followed all the necessary steps. You have created your environment using Mamba and installed the toolbox within it. So now you will be ready to go and start using the toolbox. So for that, I will open my Miniforce prompt and begin with the first command. So the first command is always to activate your environment, and for that you can use this command, Mamba activate CMT. And as you can see, I'm no longer in my base, but in my environment. Of course, CMT is the name I give to my environment. Feel free to give it the name that you wish. And now I will check for my Copernicus Marine version. For that, really simple, just type in Copernicus Marine, followed by the version option. And as you can see, I'm using the latest version, which is the 2.0 version. So now let's print some details about the describe function, the first function that I have defined. So again, always type in Copernicus Marine, which is the name of our package, Copernicus Marine Toolbox, followed by the name of the function, which is the describe function, and followed by the help option here. And as you can see, we can take a look at all the options that you can include within your request. Of course, you can use, for example, dataset ID or just I to short it. And here on the left are the options, and on the right, it's the description of each option. Of course, I'm not going to dive in detail on each option. So what I recommend to do is to go to the Help Center, type in Describe Toolbox, and you will be getting the article which speaks in details on how to use this function. So let's clean up the terminal and move on to the next one, which is the login function. Again, just type in Copernicus Marine, followed by the name of the function, which is login in this case. So now this function requires to put your credentials. So I will put my username and my password. As you can see, you won't be able to see what you are typing when it comes to the password. So make sure you type in the right one. So here, since I have already logged in, I already used this function. It's asking me to overwrite it. So just click on yes, just to show you the process. And my credential files is created in my Copernicus Marine environment. If we check it here in Copernicus Marine, and then we can see the credentials files has been created. So perfect. Let's move on to the next one, which is the get function. For that, again, we will print the details about this one. Copernicus Marine get, followed always by the help option here. And then we can see the different options that you can include. Of course, all these are optionals except for the dataset ID one. You need to put your dataset ID or simply I to specify the dataset that you need to download. For that, we're going to use an example. Just clean up, and I will use the example of the dataset that I have presented in my first presentation. This one. Just going to copy and paste the name, the dataset ID, and then use the I, as I said, to specify the dataset ID. And you can also apply the filter option here, which you will find among the options, and only download a certain period. For that, I'm just going to use the regex option. This will open the brackets, star. Let's say I want to download 2024, January 22nd to 23rd. We'll just close the regex option here. And then I can also specify my output directory just by putting the O and just going to select an output directory, the data, for example. Just going to copy the path here. And now I'm ready to download my data. Everything looks fine. So click on download. So here, as you can see, the data is being downloaded. And if we check our output directory data, then you can see that my data is indeed being downloaded for the month of January. So perfect. Now let's close this tab and move on to the next function. Of course, for this next one, I'm going to use the Python API interface, which is the subset function. So as I said, you can use the one that suits you. Personally, I use the Visual Studio Code one. And same thing, first things first is always to activate your environment, in my case, CMT here in the kernel section, and then begin with the code. So the first step is always to import the package. Import Copernicus Marine. And then we will print the details about the subset function also. And for that, just type in the name of the package, followed by the name of my function to print. And at the end, an interrogation point, which is the equivalent to the help option in the command line interface. So as you can see, also, we have various options that you can include when using the subset function. And for example, you have the output directory. You can specify the minimum latitude values, the variables. So many various options that you can explore in details within our articles in the Help Center. So now I will just give another example on how to download the data using this one. And again, I will go back to the My Ocean Viewer Pro and simply give you an example. For those who didn't intend it, that would be a glimpse on how you can use this tool. So I will just use the define on map option, go to the surface that I have created, and then automate. In here, I will be getting two different templates. I have the command line interface one, and since I'm using a Python API, so this is the one that I'm going to use. Simply copy it, go back to VS Code, and then no need to import this again. So here at the end, I can specify my output directory also. Specify the output directory. Again, just going to copy and paste path like this. And now let's download the subset. So the subset is being downloaded. It shouldn't take a long time. All right, perfect. As you can see, the data has been successfully downloaded. And if you go back to our output directory, indeed, my .NET CDF file has been downloaded. All right, let's move on to the next one. So this one don't allow you to download the data, but only remotely open it. You can though use it to post-process applications, which is called also the open data sets. This one is particularly interesting when it comes to, let's say you want to download the given data set, but you don't exactly know what it is. So you don't have to download all the data sets and then open it and proceed to delete. So you can simply explore, remotely open the data and see what the variables are. And then you can jump in and use the subset function to download it or the get function. So again, I will just use the type in this command to print the details on this one. Of course, change the name of the function to open dataset. So as you can see, you can include many various options also, except for the output directory, because the downloading process, as I said, is not included within this one. So let's simply copy this template and paste it here, because it's basically the same syntax, except changing the name, of course, of the of the function. Just give it a name here, print it, and then dataset. Of course, remove the output directory since we don't have to, we can download the data with it. We're using this one. And now we should be able to print our subset of data and take a look at the details. So here we have the dimensions, the coordinates, the variables, as well as the metadata of my subset. There is also a way to export this subset of data into a netcdf file using the open dataset one. And for that, you can use a method called toNetCDF. For that, it's really simple. Just type in the name of your created subset, followed by the method toNetCDF here, and specify your output directory where you want to store your data, like this. And just don't forget to give a name to your data file. Just call it data point NC, which is the extension, netcdf, and run the cell. So my data should now be exported to my output directory into a netcdf file. So there is a way to export your subset of data, but only by using the toNetCDF method. So let's now move on to another similar function, but this one allows us to open the data in form of data frames and also allows us to export it into a CSV file this time for those who wish to explore the data in CSV. So this one is called open read data frame. For that, just going to copy and paste the same template and change the name of the function. So in this case, read data frame, run the cell. So just keep in mind that the data is no longer available in XRA packages, but only in pandas. And make sure that before you open your data using it, you first create your subset and then open it, because otherwise you will be getting a message telling you that the amount you have selected is not supported. In this case, it's working. We have selected our subset of data, we have opened it, and as you can see, we have our data printed in data frame form. So now, as I said, we can export this data into a CSV file. And for that, we're just going to use basically the same syntax here, except changing the name of our method, because we are going to use the toCSV method, specify and change here our extension to CSV, of course. Run the cell, and we should be able to take a look and see that our data has been successfully exported into a CSV file. So perfect. I think we have covered all the main feature and option that you can include when using the various function of the toolbox. And again, if you wish to go further in your research, just go back to our site and take a look here at the user corner, for example. If you want to explore all the data that are available to be downloaded using the toolbox, go to the user notification service, and you can go here into this section, data availability on new services. And now you will be getting a table, a PDF table. This one contains all the data sets that are archivied in ARCO format and are ready to be downloaded within the subset service, because sometimes we have various requests from users that telling us that they cannot download the data, but the reason is that it's simply that the data is not ready available in the ARCO format, which means that you cannot download it using the subset service. So I think that's it for today's presentation. I hope you enjoyed it. And please, if you have any question, ask them. I would be glad to answer it. Enjoy the rest of the event, and thank you, everybody.
Thanks, Razak, for your presentation about the Copernicus Toolbox. So we have a few questions for you, and we will go to them in a few seconds. Up. So the first one being, is the Copernicus Marine Toolbox only available for Python?
Sorry, could you repeat the question?
Is the Copernicus Marine Toolbox only available for Python?
No, as I said, we have there is other ways to use the toolbox. You can use it using R, for example, using MATLAB. And for that, you can just go to our help center and type in the toolbox keyword followed by, let's say, for example, use the toolbox within R within MATLAB, and you'll be getting articles which lists and speaks on how to use it with examples, of course. But so it remains possible, yes.
Okay, thanks. The next question, what are the main differences from the Wikio Copernicus viewer, so the expert data viewer, and the Copernicus Marine Toolbox, like data sets, pinpoint, data download, versions, etc.?
I cannot exactly say the differences. And
I think the
so,
Wikio viewer is more like the MyOcean Pro viewer.
yes, I would say the same thing, since the MyOcean Pro Viewer allows you to analyze and download the data, but the user can reach out to us through the chat, and we will check in it in details and give it the best answer. So, yes.
Okay, thanks. I can put the question on the side also. Okay, technical question. I noticed the toolbox uses S3 buckets to retrieve data. Can I use the S3 bucket URLs, to retrieve the data with HTTP requests instead of using CLI or Python IPAs?
Yes, yes, indeed. We use the S3 buckets to retrieve the data. Unfortunately, you cannot access this service, since the service is reserved to us to get the data retrieved. So the users cannot access this service, unfortunately.
Okay, thanks. A more general question, can I download data from a specific time period?
Yes, it is possible. As I said, you can use the subset function for that. And within this, you have options that includes the start date and end date, which means that you can specify your time period as well as your variables that you wish to download. And yes, you can download it.
Thanks. Another technical question, can JetBrains PyCharm Community Edition be used for working with Python in this case? Is it compatible, since you mentioned that you've used Python?
Yes, PyCharm remains also a Python editor, so it's basically the same things with VS Code. If you can use the toolbox with VS Code, that I don't see any issues using PyCharm within it. So yes, I would say that you can use the toolbox using PyCharm.
Okay, thanks. So for now, that's the last question we have on the Copernicus Toolbox. I can wait a few seconds, but just to check if we have everything. But yeah, otherwise, thanks again, Rezak. And yeah, thanks again for the presentation and the short Q&A session. And we'll see you
Thank
next
you,
time.
everybody. Thank you.
Bye.
Bye.
And yeah, so we'll go to the Jupyter Notebooks tutorial, I guess. So hi, Alexandre. Yeah, so welcome, Alexandre. And yeah, whenever you want, you can start sharing your screen. Hi.
Hello, Gael. Thank you for the introduction. I'm going to share my screen and we'll be ready to go. So it should be visible right now. Okay. So thank you, everyone. So I'm Alexandre Morin from Noveltis, and I'm going to give you an overview of this notebook, which is focused on offshore wind power in the European Northwest Shelf. So wind power is quite an important topic, of course, when it comes to sustainable energy, because as the world is slowly transitioning to clean sources of energy, offshore wind power is, well, has emerged as one of the key players in the energy mix. And but of course, in order to design or even build a wind farm, there are several key factors to take into account. So, of course, the potential for energy production based on the wind data that can be available in the areas that we are interested in. But also, there are constraints of economic or technical order, installation cost, how to integrate such an infrastructure to the general electricity grid. And also, of course, environmental constraints, because of building such an infrastructure has great impacts, first on the marine ecosystems, but also on human activities, fisheries or maritime routes. And of course, such infrastructure have to be designed to withhold extreme weather risks. And so those should also be analyzed when designing such plants. So in our case, we'll be focusing on the first point, which is the potential for wind energy production. And so we will be analyzing wind data available in the Copernicus Marine Service catalog. And so this is what we're going to explore in this notebook. So we're working with Python. So here's in a list of the Python modules that we are going to use in this notebook. So if you're already familiar with Python, you probably know most of them. So NumPy is the most common one to process data arrays. With pandas, you usually process data tables, which are called data frames in Python. Xarray is the main library to process scientific data, which comes in netstf format. So this is what we're going to use to process the wind data. SciPy is mainly used to compute statistical analysis. Matplotlib and Cartopy are used to draw and plot different graphs and maps for the data visualization. And datetime is also a key library to process time series and manage datetime indexes. So here I'm working on the Copernicus Jupyter Hub. So all the libraries are available in the CMEMS kernel. So when I execute this cell, everything should be imported without any errors. And now we are ready to explore the notebook with all the libraries imported. So in this section is a brief overview of the product that we are going to use in this notebook. So it's basically a combination of model and satellite observation, which is called Global Ocean Hourly Reprocessed Sea Surface Wind and Stress from Scatterometer and Model. So you can click on the link if you do it at home to look at the dedicated Copernicus Marine Service page for the product. And you can also access the user manual or quality information document if you want to dive even deeper into the exploration of the product. But you'll find here the main variables that are available, the resolution, temporal coverage, etc. But to keep it brief, in our case, we'll be interested in the spatial resolution, which is 0.125 degrees. It has an hourly temporal resolution, and it covers from 1994 to 2024. In our case, we're only going to retrieve 1 year of data in order to keep files that are manageable in terms of size. And also 1 year is quite convenient in order to evaluate the potential of wind potential, because we will have, well, it sort of erases the internal seasonality of the data. So in order to access the data, you've already been presented the Copernicus Marine Toolbox. So here is just a brief use of it through a Jupyter Notebook. So basically here what I do is I import the Copernicus Marine Toolbox Python API. Here I define an area of interest where I want to download the data from. So as I've said, we are focused on the European Northwest Shelf. So it will be in this area here. Here you retrieve the identifier of the product on the dedicated page here in the data access section. You can find the ID here. I select my variable. So here we'll be using the eastward and northward winds, the two components, and also the air density and the time coverage that I want to retrieve. So here is the year 2023. So I've already pre-downloaded, so I will not do it again because we have only a short time to do this presentation. But here is my data set after it is downloaded. So you can see that it is in the netcdf format, and which is why we're going to use Xarray to open it. So using Xarray, that's what we are ready to explore the data set. So I open this data, and in Python, in the Jupyter Notebook, you can see that when you open the data, you have access to several information about the data set. So here you can see that the data set is in 3 dimensions. We have a latitude and longitude and time, which is what we expected. Here you can check that clicking on this icon, you can have a few samples of values. Here are the first. We can see that we go from midnight on the 1st of January 2023, and we finish at 11 p.m. on the 31st of December 2023. So we indeed have 1 year of data with 8,760 hours. We have our longitude and latitudes, which are consistent with what we have specified in the area of interest, and our variables. So clicking on this icon, you can display the metadata of the variables, with especially the unit or the long name, which can also be a description of the data. So as the only pre-processing we are going to do on this dataset is the calculation of the total wind speed, because we have the 2 components, and using a simple formula here with the Pythagoras theorem, we're going to compute the total wind speed by combining the 2 components. So it takes some time because we have a lot of data, but it should be done in a few seconds. Okay, it's taking a little longer than I expected. Okay, it's done. And so doing this simple operation, we can see that we have added a new variable to the dataset. We haven't specified any metadata, so here the icon will not display any data, any additional information. So in this section, I just quickly show how to draw a wind field. So basically, it's just a combination of 2 functions of the matplotlib library, which is the pcolor function that allows us to color the map. I I do it here. It allows us to color the map according to the wind speed. And the quiver function allows us to draw arrows according to the direction of the wind, so combining the eastward and northward components. And if we look at the map, we can see that choosing one random date here, it's yes, the 25th of September. We can see that we have displayed the wind speed here. And we can also do it as an animation to plot several consecutive dates. So this is what I do here. So it does take here a few minutes to draw all the maps that we're going to use in the animation. So I will not execute it right now, but here, for instance, you can see that I select a starting date, so 25th of September at midnight, and I plot the 48 following hours. So basically, I'm just animating the wind data over 2 entire days. So as I've already pre-executed the cell, I have all the different maps available here, and I'm just combining them into a single GIF file. So this is what I do here. And you can see here that the animation is quite consistent with the direction of the arrows that follow here this strong wind patch, which is, displaced to the east. Okay, so let's now move to energy, wind energy potential. So in this section, we are going to estimate in this area what is the potential for wind energy production. So we are going to approximate it by using this formula, which is so proportional to the kinetic energy of the wind. So the power that one wind turbine can retrieve can be approximated with this formula. So rho being here the air density. So we have this as a variable in our data set. A is the surface area that is covered by the blades of the turbine. So this can be calculated using the radius of or the length of the blade of the turbine. V is a wind speed, and C is a performance coefficient, which accounts for the fact that a wind turbine doesn't convert all of the wind power into electricity. And so it's generally between 0.4 or 0.5. So here we're going to select one of 0.45. And to compute the surface area, we are going to approximate a typical length of a wind turbine blade of 100 meters. So doing this, I can estimate the converted power over the whole data set. So this calculation also takes some time. And you can see that I combine the air density and the total wind speed here. And I add the different constants of the formula. And when I draw this on the map, this is the estimated potential power retrieved by one wind turbine over the area. And what we expected is kind of verified here, is that the further we go from the coast, the higher the potential for wind power is, especially here around Ireland. And if we do some research and look at well, the future plans or current wind farm that are that exist, here you can see that we have a lot of plans for future wind farms around Ireland, which is kind of what we expected. Also here near Scotland. So this is quite in line with our findings here over the year of 2024, 23, sorry. Okay. So in the last section, we are going to model with a little bit more precision a wind power farm. So basically, we're going to replace this approximation by a more precise model, let's say, by modeling the different regimes and phases of with different operation phases of a wind turbine. that can be sliced into 4 operating phases. So below a wind speed of 30 meters per second, the wind is considered too weak for a turbine to operate. So basically, the wind turbine doesn't spin, and so it doesn't generate any power. Then between 3 meters per second and 12 meters per second, the generated power is proportional to the cube of the wind speed. So this is quite close to the formula that we had before. And above 12 meters per second, but before 25 meters per second, so the wind turbine is operating at max power. And so it's yielding the nominal power output that is given by the manufacturer, but it can't go any higher due to mechanical limitations. And above 25 meters per second, the wind is too strong and the turbine must be stopped due to safety reasons. Of course, those constants are here arbitrarily chosen. They depend on the model of wind turbine and are usually given by the manufacturer. So those are only usual or typical thresholds that we're going to use in our model. So this regime, those different regimes are represented here. So the power is given according to the wind speed. We have several thresholds here that are defined in the function. And using this, we are going to model an entire wind farm with only a few parameters. So first, we'll be defining a model of a wind turbine, so based on the wind speed thresholds that I've described to you just before. The nominal power, which is also given by the manufacturer. So here, we are considering that our typical wind turbine, we have a power of 15 megawatts. And then our wind farm will be defined by its location, which is where we are going to sample the wind power to estimate its energy output, and the number of turbines that are in the farm. And so this is basically what we define here. So using the wind data as input and the model of the wind farm as input of the function, while the exact power output is computed using the power curve here. And those flags are also calculated in order to account for the different operating regimes, which are going to be represented in the next cell. And so in this function, I'll just prepare all the plots for my wind farm model. So here, for example, I've executed the function at a location near Ireland with 20 wind turbines. And so when I execute this and plot all the results, here is what I get over the year of 2023. So in this plot, I show the location of the wind turbine, the wind farm that I've modeled. Here is a time series of the power output. So you can see that we have a clear ceiling here, which is the stage where the wind turbines operate at max power. It's a nominal phase. And here is a recap of the parameters. So nominal power of the turbine is 15 megawatts. Here we have our different wind speed thresholds. And here is the number of wind turbines in the farm. So we have a nominal power of 20 by 15 megawatts. Here is the proportion of each operational phases. So for example, here over the year of 2023, our wind farm has operated at max power 19% of the time, and it hasn't been working around 6% of the time. And during 75% of the time, it has operated at a regime called partial load operation. So basically in a regime that is between 3 and 12 meters per second regarding wind speed. And you can see here that is quite consistent with our power output time series, with especially here a period of quite low production between, let's say, April and July 2023. And finally, we have estimated here the total energy produced over this year, which is approximately 1,200 gigawatts per hour. And with this result, you can calculate the capacity factor of the wind farm, which is the actual energy generated in proportion to the theoretical maximum energy generated if the wind farm had operated at max power over the whole year. And here we have a capacity factor of 0.46, which is quite in line with the typical capacity factors of real-life wind farms. Okay, so we are reaching the end of the presentation. Here you have a few exercises if you want to deepen the analysis. You can do the animation that we have seen before on other dates. You can create virtual farms on other locations or retrieve more wind data to see how they behave on other years on other areas. So feel free to deepen your analysis at home. So I hope you enjoyed this presentation, and I'll be happy to answer your question if you have some. Thank you very much.
Thanks a lot, Alexandre, for the nice tutorials. It was really interesting to see that. And yeah, so as you know, we have a few questions for you also. So we'll go to that part now. So the first question being, do you follow any verification process or have a specific plan in place to minimize, eliminate, or debug errors while working in Jupyter Notebook?
I'm not sure about what the user means by errors. Is it errors in the data or errors in the code?
I would say error in the code, like maybe package or something, stuff like that.
Yes. Well, I don't have a specific written defined plan when developing the notebooks. Usually, as you execute the cells on the go, if there is an error, you immediately see it. So when developing a notebook, this doesn't really raise any question, I guess.
Okay, thanks. Okay. Next question, would your approach to estimate the power generated by wind turbines on land be valid using the Copernicus Marine Wind product?
Well, if the wind product is available on land, which I think it is, well, you should not be too far from the models that we have made here. But I think that land wind turbines have different, constructions are constructed differently than the offshore ones. So you would probably have to research a little bit about the key differences between land and offshore turbines to adjust the model accordingly.
Okay, that's good to know. Good starting point.
Yeah.
Thanks.
Also, one big approximation that we have made in this notebook is that we have used wind data at 10-meter level. But of course, wind turbines, sweep the wind at least 100 meters high. So we only had surface wind in the Copernicus product, but in order to be really, really precise, you would need to have like 100-meter level wind data.
Okay, thanks. Yeah, so maybe more with the Copernicus atmosphere service, the wind data would be more practical.
Yes, probably.
Yeah. Okay, thanks. This question. If you want to work with a very large netcdf file and another data frame file, is it feasible to convert the netcdf file to a data frame to process the data together?
So Xarray indeed provides a function to convert a dataset to a data frame. I think it's just called to data frame. I would have to look it up, but I think that's the case. Although if it's a very large file, you might have trouble. I don't know if such big file can be handled as pandas data frames. I never tested that. But there is indeed a function in Xarray to convert a netcdf to a data frames in Python.
Okay, thanks. So the next two questions are still about file. Oh, but I lost one. Okay, we'll do this one and I will put the other one up. What's the best way to process a large data file? For example, 2 years of global spatial coverage for calculating new variables given computational time. I guess, isn't there like NetCDF tools, like NCO and CDO functions to process big NetCDF file available on terminal and stuff like that?
I'm not exactly sure. I mean, the last time I had to process data through NetCDF data through a command line, I had used something which was called a CDO,
Yeah.
but this was mostly for climate data, so I don't know if it would be suitable for every kind of data. It was very specific to climate data, but I don't know if the equivalent exists for marine data or something similar.
So thanks for this very cool presentation. Can you give an estimate of the size of the wind data? For example, how big would the global data across unrecorded years be? Do you know the size of the data file you use?
Yes,
Yeah.
so based on the output of the download of the Copernicus Marine Toolbox, my year of data was 4 gigabytes approximately. So this
Okay.
is quite large. So if you do this on your own, perhaps make sure to specify an area of interest that is not too big in order to well, have a manageable file size.
Yeah. And even if the file is too big, I don't know if you're just able to download it. So. Okay. I would have expected the wind product to be available on another Copernicus service, the atmosphere. Can you explain the allocation of products between services? So the wind product used by Alexandre here is above the sea, so that's why it's available in the Copernicus Marine service. But as we said earlier, for the question about wind turbines on land, to have a better approximation of the wind, you would have to go on the Copernicus atmosphere service, which provides, well, wind above land also, and also probably at better, well, at better height to do your calculation, because as we said on the Copernicus Marine service, it's on surface wind, so if you're on land, you should probably go to the Copernicus atmosphere service to have the better estimation. Okay, so for the Jupyter Notebook question, that's the only type of question. We have a few questions about the link of the tutorial, so we will put that again in the chat, so no worries about that. But yeah, well, thanks again, Alexandre. I think that's all for the question. So
Thank
thanks
you
again
very
for
much.
the question. And yeah, so for the participant, we will have a short break of 10 minutes. And we will come back after the coffee break, so feel free to discuss with each other, look at the polls, and we will also put an address email in the chat. So because if you are using the Copernicus Marine data yourself, and if you want to submit a use case like you might have seen on the first day, you are more than welcome. So feel free to do that if you are using Copernicus Marine data in your research. And yeah, see you in 10 minutes. Welcome back, everyone. So I hope you had time to take a little break and that you are ready for the rest of the workshops. And we will start with the QGIS tutorial by Daria. So welcome, Daria.
Hello. You hear me?
Yeah, we can hear you.
Okay, great. I will share my screen first. You see my screen?
You can see it,
It's all
thanks.
good. Okay, great. So, well, hello everyone. My name is Daria. I'm from Novelties, and today I will present you a short QGIS exercise, and we're gonna look at relation between ocean conditions and fish in the fort, and most importantly, we're gonna look at fish in the fort itself and seawater potential temperature. So. This is going to be quite a short version of this exercise. You're going to have a PDF file also if you want to look at it in more details, because well, we don't have time to go really like step-by-step procedure in QGIS. But to start with a little context, well, we're going to look at the fishing hours, fishing effort. It's called apparent fishing effort, which is usually calculated in hours per square kilometer. And for that, we use some external data. For example, here on this image on the slide, you can see apparent fishing hours for 12 years from 2012 to 2024, and you can see the scale here below. And we're gonna focus only on one geographical zone. We're gonna look at the China Seas. So that's this region over here. You can see that it's quite yellow, right? And on a scale, you can see that it corresponds to high fishing effort here. So I will go straight to the QGIS. And here I will show you what we did to the study. So first of all, the first exercise, there are kind of two sub-exercises, you can say. And the first one is to look at the potential seawater temperature. And this is the data that we acquire from the platform, sorry. And this is a global ocean reanalysis model. So first step was to import the data. And here, for example, we download data for 2 years. We download data for 2014 and 2024 for both seawater temperature and the fishing effort to see basically how is there any change in those variables in these 10 years. And here, for example, let me just show really quick. The data imported is, as the data is presented as an SCSV file on a platform, to import it in QGIS, we used this plugin, which is called NetCDF to GIS. This is a plugin that was developed in Novelties, and it allows more quick and more easy way of mapping NetCDF files. But you, of course, can use, let's say, native tools in QGIS. So they were mapped like this. Basically, we just had a monthly mean product. So here we have 12 layers, so from January to December of 2014. And very quickly we can look at how it changed the temperature. I will also show a scale. So from 5 to 35 degrees Celsius. And we can see that, we can see how here the ocean temperature rises with, summer months coming in, and then peaking here, and then from September cooling down again. So that's quite, coherent with a seasonal change. And another product was basically the same, just for 2024. And we can also see the same trends in warming during the summer and cooling down after. So that was expected. And what we wanted to see actually is what's the difference, let's say, between this these 2 years in terms of seawater temperature. And for that, a very good representation is so-called like interannual change, or kind of like climatology. So for that, we basically want to calculate, we have monthly means, right? So 12 values. And what we want to have yearly mean. And then have a difference between yearly mean for 2014 and yearly mean 2024. And this will give us interannual change. So this is, of course, a very simplified approach, and yeah, because between 2014 and 2024 were 10 years, right? But just to compare these 2 years without like diving deeper into all the years in between. And after we calculate it, and to calculate that, you can use, we can go to Toolbox and use raster calculator function. It's called like that. And here, basically, you can choose an expression. And for us, the expression was, well, it was quite long. I don't think I will set it up, but basically, it's a sum of all monthly means for 2014, right? So January plus February plus March, blah, blah, blah. Then you divide it by 12, well, simply mean, right? And we do the same for 2024. And then from 2014, the value, this yearly mean 2014 minus yearly mean 2024. And like this, you put this big expression here by basically choosing your layers like that. And it will give us something like this. I'll also show you a scale with -3 to 3. So here we have our interannual change. Also, let me maybe close it. So we have positive and negative values. And here we see that, well, the red values, the positive, here explicitly they are showing us warming. No, sorry, not warming, the opposite. You have a cooling trend, meaning that in the red areas, well, they're not super red, they're like slightly red. It means that between these 10 years, there's been a cooling. So it means that in 2024, the seawater temperature in these regions were cooler than in 2014. And the blue means the opposite, so it means warmer. So of course, with all the climate change and what we experience right now, we expect generally to see more warming trend, and that's exactly what we see here. We see more blues than reds, and while in here in the south part, we see mostly kind of whitish, we will say, and white means values close to 0, meaning that there's been no significant change in temperature. And of course, that's as I said, quite simplified approach, because we looked only on 2 years with like 10 years in between, which we omitted. So that was just to see the most impacted, let's say, areas by the change in the seawater temperature. And I see that the most impacted ones are this bay and this area here with a cooling trend. And well, here mostly around here we have a warming trend. So with water being warmer in 2024. So the next exercise, we wanted to look at the fishing effort. And as I said, fishing effort is measured in hours per square kilometer per zone. So it's meaning by hours, meaning how much time fishing vessels, fishing ships spent well, doing fishing activity in this exact region. And this is the data provided by I think it's called Global, I will check it very quick, Global Fishing Watch. That's a website that provides all this information like globally. You can go there and check their website. The link is also provided in a PDF file. And what we did is, of course, we wanted to have our we decided to focus only on 1 month. For example, we decided to look at the month of June for both of the years. June is this one. For example, here this is June 2014. And if we compare to June 2024, we see that, well, in June 2024, seawater temperature generally was higher than in 2014. And we decided to just choose this random month, let's say, but you of course can look at the different months and maybe at all of them. So we downloaded data for fishing hours for 2014, June, and 2024, also June. And here you can see this is a raster layer. And here you can see the pixels, basically, which are corresponding, if we zoom really, corresponding to the zones with fishing hours. So with 0 being in blue and, well, in red being 1,000 hours, let's say. So here we can see the most used, let's say, zones for fishing. And if we look at 2024, we'll see a much bigger picture. We see that there are much more data here, with also very peaking red spots here, for example. And we can even verify how the value of this pixel by choosing this. Sorry, I don't see this little tool. Zoom is blocking it. Oh yes, thank you. So this tool, which is basically information tool, we click on it, and well, it shows us for our layer. It shows us what 5,400 hours. That's a lot. And like this, you also can like check, I don't know, this one, for example, which is only 17, which is very nice tool to do such verifications. So we can see that, yes, we have much more data. We have much more fishing effort in the region, which could be related to many reasons. It could be because, well, first of all, maybe there's more data now. There are more tracking on ships. So before we just didn't have this type of tracking, this type of tools. But it also can be related, of course, to what we do use this area much more than before. So what we wanted to see here is to have statistics about this. So like now we have a lot of pretty images, pretty pixels, but we don't know much information from it. So we want to see what data it can actually give us. And there is such a tool in QGIS, which is called, wait, let me just it's called raster layer statistics, which can give you statistics of a raster layer. But there's also a possibility to have statistics for a vector layer, and that's a basic statistic for fields. And we decided to do both to see the difference in data it can provide. But before, what we did is we filtered, sorry, not filtered yet, but we vectorized our raster layers to vector layers with conversion polygonize function. And here, for example, well, you don't see much because I already filtered it. If I, okay, so that was original vectorized layer. So if you compare it to raster, it's basically the same, only the values change a bit because, well, the style is a bit different, but well, the values are the same, just to represent it differently. And the same for the fishing effort for 2024 for June. And here you can see, for example, what we do not see all of the picture because we put a filter. We filtered it here by clicking on it, and we filtered it as hours, more or less, more or equal to 720, which is basically what we are asking for. Only the zones that were used basically for the whole month of June. So if I remove this layer, we see that, filter, right? And if I want to filter, right click here, put filter and put this one. And you can see that basically there are just few zones, mostly along the coast, that were used for fishing for like during the whole month of June, and well, more than that. So that was for the filtering. And the function what I told you about is these two functions for statistics. Then you use them. Here you put input layer and then fields to calculate, and then you save it to a file. And this is actually giving you an HTML file, so it's not exactly in QGIS. Let me see what it gives. So yeah, the results will be such such HTML files here. And let me see if I actually can open it. Oh, nope. Okay, it didn't work as I wanted it to work. Okay, I hope you see my screen. And here, for example, this is a report that QGIS is producing. And here it's for, well, raster statistics for 2014. And here we have a minimum value, maximum one, range, sum, mean value, standard deviation, and so on. So we can see that the maximum value was 2,100. But the mean is 48 and standard deviation 120, which kind of shows us that fishing activity was kind of moderate in this region. And that was for 2014. And if we open the same one I have for 2024, right, we see that well, minimum value is still 0, but the maximum value is actually 82,000, which is a huge number comparing to 2,000. But the mean value is 98. Of course, it's higher than the previous one, but still like kind of low, we'd say. Well, standard deviation is 848. That was for raster layer statistics. So this is this tool, raster statistics. And another tool is basic statistics for fields. So it's the same tool, just for vector layers, not for raster layers. And the result it gives us, let me open it. So that's what it gives. And you can see that there are more fields here. And if I compare it to, what was it, 2014? So it's this one, right? Yep. Oop. Wait. Like this. Yeah. So here what we can see is minimum value, maximum value, yes, all that. We can see that we have now median value, which is also very representative. We also have minority, so rarest occurring value, and majority, most frequently occurring value. And we actually see that most frequently occurring value is 1, so 1 hour, which is that's kind of, how to say, we can see it, I think, here. Right, we can see that we have a lot of blue pixels here. And so yeah, we see that for vector fields, this tool gives us more information, more outputs. But what we also can notice is that it actually does the rounding, so like approximation, because for raster layer we have a maximum value with like a lot of digits after a point. And for vectors, we have it just rounded to 2,142, you know. And because of that rounding, of course, it rounds, it also impacts mean value. Like here, mean value is bigger, it's 51 comparing to 48. And same for like standard deviation. For example, we see that it's 123 comparing to 120. So yeah, overall, we can see the difference between two tools that allow us to calculate statistics on a raster and vector layers. Of course, that depends on what kind of information, what kind of data you have. Is it raster layers or vector layers? If it is pertinent to transfer to like to convert from raster to vector layer, because it also can be time consuming and can be also very bulky for QGIS to process. But using these two tools, you can access statistics of layers. So that was for the second exercise. And I think that's all for me. If you have any questions.
Thanks, Daria, for the presentation. And yeah, we have a few questions for you. So thanks again for the live demo of the tutorial. And we will go to the Q&A.
I should stop my, yep.
It's okay, thanks. The first question being, I wanted to know how you downloaded the layers and if you could use the WMTS server.
Well, the data well, there are two data, right? Data from Copernicus Marine Service was being downloaded through data store, basically by usual, like visual request. You know, I didn't use Jupyter Notebook or anything else. And for the other data, the efficient effort, well, you go to the website of the external website, and it's quite clearly stated how to do it. So yeah.
Thanks. Next question, more open question. Does the ocean temperature really reach 35 degrees, or do I need to interpret details? Sorry, I don't remember how to say this.
Well, as it shows, but yes, it does. I mean, we saw that in some regions, well, I can double check it, but in some regions we had clearly very high values, but of course, well, the color scale was from blue to red, right? And on the on the image on the layer, we saw that some zones were mostly orange than red. So yeah, maybe there were some very small areas that was reaching 35, but mostly I think it was just below it. But yeah, it's just also it's a scale, right? From like what 5 to 35, it's what we chose just to have the presentation more or less, to have like colder and warmer areas. But of course, you can adjust your scale bar, so it's like well, from I don't know 5 to 27 or whatever.
Okay, thanks. Okay, the next question. The data for the China Sea and Mariana Trench suggests that one should take into account vertical currents, which would require couplings to geodesics and other scientific disciplines.
Well, first of all, I'm not sure if it's a question.
I think
but
it's like, would it be interesting to use like vertical currents?
Yeah, I mean, here we don't look very in depth of the phenomena, right, or in depth like study analysis of a zone. Of course, like for example, also this is temperature, sea surface temperature, and of course temperature changes with depth, and well, with currents. Currents also influence it, but yeah, I guess you can pump it up with much more information and different variables to have a very elaborate analysis. So yeah.
Yeah. Okay, thanks. So next question. What is meant by vectors? Are they vectors in the physical sense or a data science sense?
Vectors here, that means just the data representation, like, well, in terms of how to say, well, it's a raster image or vector image, right? The same like we have in images on our computers, right? So basically, well, raster image, raster layers here means basically, well, it's like in pixels, right? So the way it is presented in the way it was downloaded, for example, from Copernicus Marine data store or from the external website. And vectors, it's basically instead of pixels, we have a polygon. So for each pixel is now not just some I don't know, some image. Now it's a polygon, so it's a geometry. Well, because it's pixel, it's just a square, you know. But your polygons also can be, well, different shapes and stuff.
Okay, thanks. It's clear. Thanks. Next question. Is it possible to view and analyze all layers at once, or can you only do so one layer at a time?
Well, you can, of course, overlap layers, one on top of another. It also depends, well, if your layers are covering exactly the same region, of course, we're gonna like overlap and you won't see another one underneath. But for example, vector layers on top of raster, you like, for example, efficient effort on top of seawater temperature, we can clearly see it. But also you can adjust transparency of your layers. So like this, you can maybe have several layers altogether.
Okay, thanks. Another question. How do satellite detect fishing fleets correlate with declining chlorophyll concentrations or primary productivity? Does it only depend on sea temperature?
Of course, it does not depend only on sea temperature. There are a lot of different variables in this equation, and yeah, of course, it also depends on chlorophyll concentrations or primary productivity and so on. So yeah, well, we don't have much time to study everything all at once, but yeah, of course, you actually can repeat the same tutorial by adding more variables and look how it all correlates together. And how do fish and fleas correlate? Well, if we have less, well, if there is less primary productivity, there is less food in the ocean, right? In the region. So of course, well, fish also could be. There will be less fish, or they're gonna migrate somewhere else, and of course it all depends. But yeah, not only on sea temperature, of course.
Thanks. And I guess that answered the next question, which is how do you interpret these results? Is there any correlation or even causation?
So yeah, that's kind of what I already mentioned, and I also mentioned before. But we see that, for example, in between this 2014 2024, we have 10 years of difference, and we see that they have much more fishing ships activity in the region, which can be, as I said, due to the fact that well, you just didn't have technologies enough, like developed enough to track all the ships, or because we really started to fish more in this region. And correlating to temperature, of course, it's not in-depth analysis, right? So we cannot say for sure, like, okay, we see that the ocean did warm up a bit on these regions, so it can influence the fishing. We just wanted to show how to do this interannual change, and also that this could be potential cause of a change in the fishing. But we see that we cannot do. We cannot draw a very particular conclusion, of course, from such a surface level analysis.
Okay, thanks a lot. And so for now, that's the last question about the tutorial on QGIS. Is there any prior license needed for the software, meaning QGIS?
No, QGIS, it's an open source tool. So you just go to the website, you download any version you like, very different versions, and that's all. It's ready to go, and
it's free.
It's completely free. It's very, very
Okay.
useful. There's a lot of nice tools and functionality there.
Okay, thanks a lot. So I think that was the last question regarding the tutorial. The other question being a bit more general, I will put some links for you, so no worries about that. And yeah, thanks again, Daria, for the tutorial. And see you. And yeah, so now we will go to the last tutorial of the day, which is the RStudio tutorial. So Simon, whenever you want, you can come in and start the presentation.
Yes. Do
I
you hear me?
can hear you. I can't see you, but
Yes. Oh, do you see my
yeah,
screen?
no, it's okay. And we see your screen also.
Yes, okay, thank you. So, hello everyone. My name is Simon Millet. I'm a scientific engineer at Novartis in France, and I will be your trainers during this session in R. So, we will use the Jupyter Notebook here to see marine heat wave in August 2024 in Mediterranean Sea in R. You will have a closer look of CMM's product, their structures, format, variable, and how to explore and plot them. So after exploring the netted file, we will make a basic plot, a basic map. Then we will make a monthly anomaly map of temperature, sea surface temperature, monthly anomaly map of salinity, and then we receive the impact of marine heat wave on dissolved oxygen. So this training focus on marine heat wave of summer 2024 in Mediterranean Sea, with surface temperature reaching 29 degrees, which is 2.7 degrees above the average. And this marine heat wave have a significant ecological impact on marine ecosystem. They cause mass mortality among various species and affecting coastline at all depths. So the rise in temperature reduces the solubility of oxygen in water, leading to a decrease in dissolved oxygen level. So this string will allow to see the evolution of different parameters, sea surface temperature, sea surface salinity, dissolved oxygen and dissolved oxygen over time. So first, the Jupyter Notebook must be set up with all necessary available libraries. So for this training, we will use the 7 libraries. There is ggplot2, that is for creating graphic, dplyr for manipulating data, rcolorborwer, this is for color palette in plot, netcdf4, it is an interface for netcdf file format. Gridesite is to arranging multiple plot on a page. Lubricate, it is to manipulating date-time data. And SF, it is to manipulating geospatial data. So first we load all the libraries. But in this training, all the libraries are already installed. But if you use another support, you can use this command line here to download all the libraries. So in this notebook, all the data are already downloaded in the folder data here. But you can download if you want the data in the Copernicus Marine Data Store. So here, where there is a multiple filter in the area, variable, etc. You can explore. But in this training, we will use 6 data sets. The first is meta-analysis physical analysis. So we use a monthly means from 30 years. The second, it is meta-analysis resolution L4 sea surface temperature. It is a daily value of sea surface temperature in August 2024. Then it is for dissolved oxygen. Here it is the analysis and forecast to have 2024, the year 2024. And here it is the reanalysis to have the past, the 30 years past of data. But if you want to download, it is possible. You need to have your own Copernicus credential, so username and password. And if you have not, you can create an account here. So first, we will work with sea surface temperature, the monthly means. So first, we set the path of the file. We load the netcd file, and you can see here the characteristic of the data set. So there is one variable that is theta O, this is the temperature. Then there is a 4 dimension, time, depth. The size is only 1 because we use only the surface. Latitude, longitude, and here it is a global attribute to have more information about the dataset. So we load all the data. It is possible to have information on the dimension of variable, for example, temperature. That is dependent on longitude, latitude, and time, or a value for a specific longitude, latitude, and time. Here it is 14 degrees. It is possible to visualize the time too, but you can see the time variable, it is a number, not a date. So to convert the number to a date, we use this function as POSIX, where we put the variable time and the origin. So here it is the 1st January 1970. So the origin is noted in the dataset in the characteristic of the variable time here. That is here the second since January 1970. So here now we convert. So you can see it is now in a date, not a number. Here it is for memory. So now we will make a basic map of sea surface temperature. So first we determine the figure size, then we create a data frame. So that depends on longitude, latitude, and temperature on a specific time. We use the index. Here it is 8. So you can see visualize the data frame. So it depends on longitude, latitude, and temperature. Here there is only none because for this longitude and latitude, it is in the land and not in the sea. Then we plot the map. So we use a ggplot function. To add the sea surface temperature data, we use geomtile. We put the data frame and the name of the column longitude, latitude, and temperature. Here it is global option of aesthetic option. Here for color bar, here aesthetic, here for the title, subtitle, here for the size of the text. Here to adjust the size of the color bar, and this one to maintain the proportion between longitude and latitude. And finally, we save the figure in the folder figure here. So we make the map. So it is a monthly mean of August 1992 of the sea surface temperature. We see that the temperature is homogeneous in open sea around 26 degrees approximately, but lower in the French coast around 22.5 degrees. So now we have seen how to make a basic map, but that is interesting. It is to see the temperature during the summer months of 2024, for example, for one day, compared to the seasonal normal. So for this, we first make a monthly average of 30 years. Then we compare to one date that is in August 15, 2024. So here we create a data frame, but here dependent of longitude, latitude, and time. And we create a column months to column months. So if it is in January, it is 1. It is in February, it is 2, etc. And here you can see the data set frame. So longitude, latitude, time, temperature, and months. The next cell calculate the monthly average. So for a specific longitude, a combination of longitude, latitude, and months, we do the mean of temperature. And then we convert the temperature to a data frame. So now we have value of monthly means for each point. Now we will work with the year 2024, especially for August 15, 2024. So first we load the new data set. We search the index of the nearest date of the 15 August 2028. So it is the index 15, and we create a data frame of this date. So here you can see you put the index. So here this data frame dependent of longitude, latitude, and temperature, not on the date. Then we use the monthly mean data set because we do a monthly means before, but for all of the months, now we will use only the August, so we subset the data frame. And then we the longitude and latitude variable of monthly means August and for this data frame are not the same. So we search the nearest Ingbor method. So first we convert the two datasets into the spatial object. And then we search we combine the two datasets. So now we see for longitude, latitude, you have the temperature of one day, that is 15 August 2024, and the mean temperature of August of 30 years. We do the difference between the two columns to have the anomaly. So you can see now we have the anomaly column. Then we plot the anomaly map of temperature. So it is the same the same code that we have seen before for the basic map. So here it is the sea surface temperature anomaly in degrees between August average and August 15, 2024. So we see the maps is almost all in red. So that so the temperature, sea surface temperature is well above normal in August 15, 2024. Especially in the northeast part of the map was the most impact with temperature more than 4 degrees higher than normal. It is possible to have a simple statistic on the map. So here we calculate the average anomaly of sea surface temperature. It is 2.1 degrees. The maximum anomaly it is 6 above 6 degrees, and the minimum is below 0.2. That is very low. But if you want to test, you have an option. If you want to test over day to see the evolution of sea surface temperature anomaly in August 2024. For example, test the 1st of August or at the end of August. Now we will see the anomaly map of salinity. So for this, we do the same that we have done before, but for salinity. And we compare the August 2024 to the monthly average of August in 30 years. So first, we load the 2024 years of salinity. We create a data frame. Here it is for the 30 years. We do the 30 years of salinity. We do the mean of the monthly means. It is the same method that we have seen before. And here we combine the two data frame. So we select the index, the month index that is 8 for August. And we do the anomaly of salinity with this difference. So now we have longitude, latitude, time, the salinity of August 2024, and the mean salinity of August, and the anomaly. Then we plot for the anomaly salinity of August 2024. So we can see the anomaly of salinity. We see two locations. First, here in the east part of the Mediterranean Sea, where it is higher than normal, partly due to increase of evaporation, and the west part here, with a lower value of salinity than normal. It is possible to test over months, like July or September, to see the evolution of sea surface salinity. Now we will see the impact of marine heat wave on dissolved oxygen. So it is in 1 point. So first we load the data set. So we want to study in 1 point near Nice in France. So here it is the latitude and longitude coordinate. We choose the nearest coordinate of the dataset. So here it is the coordinate that we want. Here it is the coordinate that we study. We create a data frame. So with the date, the dissolved oxygen and the month, because we use the specific latitude and longitude. We do now the monthly value of dissolved oxygen between these two dates. So we load another data set. We find the index of the nearest coordinate, and we create the new data frame, and we do the monthly means. So here we have only 12 value. It is for each month because we work only in 1 point. So here we plot a time series of dissolved oxygen. We merge in the data frame here. So we can see the dissolved oxygen here and the mean. It is the same for the 1 month. So it is one value for all the January, one value for all February, etc. And then we plot the time series. So here we use a geom line. We will put the dissolved oxygen. Here the mean of dissolved oxygen. So there is 2 lines. And here it is for aesthetic option. So we can see here the time series. In red it is the monthly means, and in blue it is the dissolved oxygen in 2024. And we can see from January to July, the dissolved oxygen is similar to the monthly means, but from July to October, we have a significant gap of dissolved oxygen due to the increase of sea surface temperature. So this decrease in dissolved oxygen cause marine organisms to suffocate and disrupting food chain on ecosystem. So there is an impact of the ecosystem of this area. So now the training is finished. I hope you enjoy this training. If you have a question, do not hesitate.
Thanks, Simon, for the presentation. And yeah, we have a few, not that much question about the tutorials, but a few.
Yes.
Sorry. The first question being, how do we visualize correlations between multiple variables in air? Example, using a heat map or pair plot. Is there any coding or function for this?
Alors, how do visualize correlation between? So I use so to have a correlation, we use the same longitude and latitude for each data set to have the similar coordinate and to do anomaly map. So we use a function, I don't remember the name, but we choose the nearest neighbor of the two datasets.
Okay. Okay, thanks. And do you know if there is a predefined function to do that, or do you have to code it yourself if you want to study this?
It is a predefined function.
Okay, okay, thanks. Good to know. So for all of the presenter, or just two depending on the other, how many days were the coding and debugging per study, and what equipment were used for all analysis?
So to make the presentation, we search first the topic, and then we create the code. So we are familiar with R for me, and it take 1 day to make the code and debug the code if there is some problem.
Okay, okay, thanks. So quick. Okay, the next question, I don't know if you know that. Could the generative AI data cleaning process be carried out using tools like Gemini AI and ChatGPT in conjunction with RStudio?
It is possible to use some AI like ChatGPT, but it is a help. But we should have some knowledge of coding to show the variable, the topic. So
Okay.
it is a help. It is a help. Yes.
Okay, okay, thanks. Okay, that was the last question concerning the RStudio tutorial. We can wait a few seconds, but I think that's it, basically. Yeah, so thanks again for the tutorials in the short Q&A session. And yeah, we put available the tutorial on the chat for people if they want to try. And yeah, so we are reaching the end of today's session. So for the participant, I hope it was interesting for you and that you could learn a little bit more about what the Copernicus Marine Service is about. And yeah, so also, before we go, I just want to remind you that the tutorials and the full video demonstrations are available on the webpage event on the webpage event of this event, and they will also be made available on the Copernicus Marine Service website with all of the other tutorials. So if you want to go have a look, don't hesitate. And yeah, as a reminder also, if you could take a few minutes of your time to fill in the survey we made for this workshop, it would be really nice of you. So thanks in advance. And concerning the replays, it will be made available during the day, so no worries about that. Everything from day one is already there. So yeah, you will also receive a certificate of participation, and thank you all again for your presence, and we will see you in the next training session. See you soon.